DC motor is an electric motor that runs on direct current power. In an electric motor, the operation is depend upon simple electromagnetism. A current carrying conductor generates a magnetic field. When this is then placed in an external magnetic field, it will encounter a force of proportional to the current in the conductor and to the strength of the external magnetic field. It is a device that converts electrical energy to mechanical energy. It works on the fact that a current carrying conductor placed in a magnetic field experiences a force that it causes to rotate with respect to its original position. Practical DC motor consists of field windings to provide the magnetic flux and armature which acts as a conductor. The construction of the DC motor is shown in this slide. It is very important to know that it's designed before knowing its working. The essential parts of this motor include armature as well as a stator. The armature coil is the rotational part, whereas the stationary part is the stator. In this, the armature coil is connected towards the DC supply and which includes the brushes as well as the commutators. The main function of the commutator is to convert the AC to DC, which is induced in the armature. The flow of current can be supplied by using the brush from the motor's rotary part towards the inactive outside the load. The arrangement of the armature can be done between the two poles of the electromagnet or permanent magnet. DC motor parts. There are different popular designs of the motors that are available, like a brushless permanent magnet series compound shunt, otherwise stabilized shunt. In general, the parts of the DC motor are the same in these popular designs, but the whole operation of this is the same. The main parts of the DC motor: stator. A stationary part like a stator is one of the parts in the DC motor parts, which includes the field windings. The main function of this is to get the supply. Next component, rotor. The rotor is the dynamic part of the motor. It is used to create the mechanical revolutions of the unit. Next one, brushes. Brushes using a commutator mainly work as a bridge to fix the stationary electrical circuit towards the rotor. Next one, commutator. It is a split ring that is designed with copper segments. It is also one of the most essential part of the DC motor. Field windings. These windings are made with coils, fixed coils, which are known as a copper wires. These windings round approximately the slots carried through the pole shoes. Next, armature windings. The construction of these windings in the DC motor is two types, like lap and wave. Next component is the yoke. A magnetic frame like a yoke is designed with cast iron or cast steel. Sometimes it works like a guard. Next component is the poles. Poles in the motor include two main parts like pole core as well as pole shoes. These essential parts are connected together through hydraulic force and are connected to the yoke. Next one, the slot or teeth. The non-conducting slot liners are frequently jammed among the slot walls as well as coils for safety from scratch, mechanical support and additional electrical insulation. The magnetic material between the slots is called teeth. Next one is the motor housing. The housing of the motor gives support to the brushes, bearings and the iron core. Next, coming to the working principle of the motor. An electrical machine that is used to convert the energy from electrical to the mechanical is known as a DC motor. The DC motor working principle is that when a current carrying conductor is located within the magnetic field, then it experiences a mechanical force. This force direction can be decided by Fleming's left-hand rule as well as its magnitude. A DC motor is an electrical machine that converts electrical energy into mechanical energy. In a DC motor, the input electrical energy is the direct current which is transformed into the mechanical rotation. In this video, Let us know how a DC motor working condition represented in this particular video here. A DC motor is defined as a class of electrical motors that converts direct current electrical energy into mechanical energy. From this definition, we can conclude that any electric motor that is operated using direct current or DC is called DC motor. We will understand the DC motor construction and how the DC motor converts the supplied DC electrical energy into mechanical energy in this section. In this particular slide, a magnetic field arises in the air gap when the field coil of the DC motor is energized. The created magnetic field is in direction of radii of armature. The magnetic field enters the armature from the north pole side of the field coil and exits the armature from the field coil of the south pole. The conductors located in the other pole are subjected to a force of the same intensity but in the opposite direction. These two opposing forces create a torque that causes the motor armature to rotate. The starting from the particular case here is the current in the left hand part of the coil causes a downward force and the current in the right hand part of the coil causes an upward force. The coil rotates in clockwise direction. When the coil is vertical, it moves parallel to the magnetic field and producing no force. This would tend to make the motor come to a stop, but two features of the coil continuously continue rotating here. A momentum of the motor causes it to continue to rotate as a little. A split ring commutator changes the current direction every half turn. This means that the current in the left hand part of the coil still causes a downward force and the current in the right hand part of the coil still causes the upward force. Now here is the Fleming's left hand rule. It is found that whenever a current carrying conductor is kept in a magnetic field, a force on that particular conductor in a direction perpendicular to the both directions of the current and the magnetic field. In this particular concentration, we represented the direction of the force can be found using Fleming's left hand rule. Hold your thumb, forefinger and second finger at right angle to each other. The forefinger is lined up with the magnetic field lines pointing from north to south. The second finger is lined up to with the current pointing from the positive to negative. The thumb shows the direction of the motor effort force on the current carrying conductor. It is in fact various with the variation of the angle alpha to obtain the variation of the torque and the principle behind the rotation of the motor. Let us do the stepwise analysis in this particular case. In step 1, initially considering the armature is in its starting point or reference position where the angle alpha equal to 0. Since alpha equal to 0, the term cos alpha equal to 1 or maximum value, hence the torque at this position is maximum given by and BIL. This is high starting torque helps to overcoming the initial inertia of rest of the armature and set it into the rotation. Step 2. Once the armature is set in motion, the angle alpha between the actual position of the armature and its reference initial position goes on increasing with the path of its rotation until it becomes 90 degree from its initial position. Consequently, The term cos alpha increases and also the value of the torque. The torque is in case is given BAL cos alpha, which is less than the BAL when alpha is greater than 0 degree. Coming to the step 3, in the path of the rotation of the armature, a point is reached where the actual position of the rotor is exactly perpendicular to its initial position. That is alpha equal to 90 degrees. And as a result, the term cos alpha equal to 0, the torque acting on the conductor at this position is given. So that is virtually no rotating torque acts on the armature at this particular instant, but still the armature does not come to a standstill. This is because of the fact that the operation of the DC motor has been energized in such a way that the inertia of the motion of this particular point is just enough to overcome this point to null torque here. Once the rotor crosses over this position, the angle between the axial position of the armature and initial plane against increases the torque starting acting on it. When the conductor moves to the first position rotating in the clockwise direction, it cuts the uniform magnetic field at an angle up to the 30 degree. The EMF induced in this upward movement of the conductor with respect to an external load will be the positive and will amount to the 50% of the maximum induced voltage. The change in voltage is shown in that particular here. That meaning is when the conductor moves from position 1 to 2 and there is a rotation in that particular movement of this one. So now here is, in this case here, if the rotation of the coil is from 0 to 90, 90 to 120, 120 to 180, 180, 270 and 360 degree. In this particular rotation, the magnetic field cuts in the by using the coil is varies here. By the using of this coil is varies. That meaning that here is a sinusoidal wave shape is produced by the conductor rotating in the theoretically uniform field in which the air gap is not constant because of the straight pole sides. If the pole tips are caused so that the pole face produces the uniform gap and flux density except in the inner polar regions, the wave shape of the induced here tends to flat topped here. The simple split ring commutator shown consists of the two segments and secured to the insulated from armature shaft and from each other as well. Each conducting commutator segments is connected respectively to a coil side. Since both the coil side and commutator segments are fastened mechanically the same shaft, the action of the mechanical rotation is reversed. The armature coil and connections of the stationary external circuit of the same instant that the induced reverse in the armature coil side. The fixed brushes are arranged to contact the commutator segments here. In effect, therefore, the action of the commutator is to reverse the connections to the external circuit simultaneously and the same instant the direction of EMF reverse in each of the coil side. Each brush, positive or negative respectively, it always maintained, therefore, at the same polarity. It may be noted that a single turn armature coil, which is quite small in magnitude, therefore the coil employs in the commercial machines consists of the several turns in series, thereby increasing the magnitude of the represented concept in the direct proportional to the number of the turns in the coil. In the DC motor, when the armature rotates, the conductors on it cut the lines of force of the magnetic field in which they are revolved, so that an EMF is induced in the armature as in the generator. The induced EMF acts in opposition to the current in the machine and therefore to the applied voltage, so that it is customarily and referred to this voltage as back EMF. That this is no so can be deduced by the Lenz law, and this law states that the direction of an induced EMF in such as to oppose the causing change of causing it, and which is of course the applied voltage. The magnitude of the back EMF or counter EMF can be calculated by using the formula for the induced EMF in the generator, and it is important in case of the motor to appreciate that this is a proportional to the product of the flux and the speed, and thus EB denoted the back EMF, and phi flux n is the speed may be written as EB equal to K phi n, where K is the number of depending on nature of the armature windings. The value of the back EMF is always less than the applied voltage through the differential is small when machine is running under the normal conditions. And this is the difference between the two quantities which is actually drives the current through the resistance of the armature current. In this particular, when the brushes are on neutral axis, all the armature conductors lying under the north pole carry the currents is given direction, while those lying under the south pole carry the currents in the reverse direction. The commutator serves to reverse the current in each armature coil at the instant it passes through the neutral axis. So, and this relation is always maintained as the armature rotates. All the conductors under north pole carry inward flowing currents which react with the air gap flux to produce downward acting forces and counterclockwise torque. Similarly, the conductors under the south pole carry outward flowing currents which produces the upward acting forces. These forces also gives rise to counterclockwise torques. If the air gap flux is assumed to be rapidly directed in all the points, each of the force acts tangentially and produces a turning moment equal to the force multiplied by its lever arm. The radial distance from the center of the conductor to the center of the shaft.